So now I'd like to introduce our speaker for tonight, Dr. Francis Su. He got his PhD from Harvard University, and he's a Benedictine Harwood Professor of Mathematics at Harvey Mudd University. And he's also the former president of the Mathematical Association of America. His main research area is combinatorics, but he's also particularly known for his work in fair division. Please join me in welcoming Dr. Su.
Thank you very much. It's a pleasure to be here. I had the pleasure of being on sabbatical here at Caltech many years ago, and it was a fun experience. I got to know a little bit of the Caltech community. So tonight we're going to talk a little bit about the relationship between math and faith, at least from a personal perspective. And just to be clear, I am not speaking as a representative of the Mathematical Association of America or any other body. But just as a human being like you who wrestles with questions about life and meaning and purpose and faith. I think the basic question that underlies my own quest for religious faith is a question that in some form everybody asks. Is there an ultimate good in this world? Is there hope? Does my existence here have meaning? And that was initially how I came to faith. So I grew up in a small town in South Texas. I did not grow up in a religious household. My parents were immigrants from China, and my family lived in this small town because my dad was a college professor at the local university. I didn't think much about faith questions at all. And then right before college, my father got cancer and my mother started showing signs of Lou Gehrig's disease, which, as you may know, it also goes by the name ALS. And so I was suddenly in a position where I was wrestling with big life questions about life and death and thinking about my parents. And so that was a sort of a crisis point for me, going off to college and worrying about some of these bigger questions. I began to question whether college was worth the effort I was putting in, if all that happens is we live and die and that's it. So is there an ultimate good in this world? Is there a hope that we can have? So part of what attracted me to become a follower of Jesus is that I was attracted by the message of hope. That there is indeed ultimately some good in this world. That's what the Christian faith talks about. And that this hope is not just in the here and now, but there is an eternal goodness and truth to be found in the humble person of Jesus, this person of ultimate significance. And another piece of why I became a Christian my freshman year in college was that I met Christians for the very first time who seemed to be living life differently. And this was quite different from the cultural Christianity that I'd grown up with in the South. And by cultural Christianity, I mean people who are Christians just because they've always grown up in this culture, the family's Christian, but don't necessarily have an active relationship with Jesus. So that's a little bit about my personal journey, and I won't be talking much more about that tonight, though I'm happy to answer questions about that. But what I will talk about is the relationship that I see between mathematics and faith. Mathematics, this subject that I love and enjoy, and I hope you love and enjoy too. And my own questions that I wrestle with in my faith. Do these two things relate? Do they have any connection to one another? Well, it is clear in some ways that math and faith relate. Certainly I experience it all the time because when people find out that I'm a mathematician, they often feel the need to confess. So I often think of being a mathematician as a bit like being a priest, right? People often come up to me and say, I was so bad at math. It happens a lot. And, you know, it's a funny joke, but it's an interesting question. Why is that a funny joke? What does this joke say about people's relationship with math? There's a question. Take a moment to discuss that with your neighbor. Yes, meet your neighbor. Say hi to your neighbor. Yeah, the question is, why do people feel the need to? Why do people feel the need to confess that they don't, that they weren't good at math?
Maybe you don't feel the confess because you're good at
More like so usually they say something about math, which is like other bad. Or I mean, if you're a math kid, you're not considered bad at math. You're like competed in math competition. So I think it's like a desirable connection.
When you see the math union, you notice how hard you're working out.
So quick answers. Give everybody a chance to say something.
So of course I can't really learn a math and math teacher, so and if I already do myself at all, ask them math question and how many
Okay. All right. Let's wrap it up and come back together. All right, I'd love to hear from any of the tables here some potential answers to that question. Why do people feel the need to confess that they're not good at math? Any takers? Any volunteers? Don't be bashful.
Feels like an objective measure of intelligence.
Feels like some kind of objective measure of intelligence. What else? Yes.
I think people just want to relate to you, so they have nothing else to say about their mathematics experience, right? So, I was bad at it in high school, right? But if they're like if they did math competitions in high school or something, they're not gonna say that they're bad. They're gonna be like, oh, I did like the AMC when I was in high school, like.
Okay. Yeah. Good. So it comes from a need to relate in some way, even if it's like an antagonistic relationship, right? Yeah. But let me push back a little bit on that, right? Like if you were an athlete, and you know you met, or maybe you met a great athlete, would you say, I was so bad at track and field? Good question. Yes, back there.
High school math is sort of a universal experience we all went through. Sort of a universal rite of passage.
Oh yeah, universal rite of passage. So people feel the need to confess because it's a way of connecting, or
Yeah, in some sense. It's like I did it too. I may not have been as good as you were, but I did it, so I did it as well.
yeah, okay. One more back here.
I feel like in a way it's kind of stigmatized. Sorry, I feel like in a way it's kind of stigmatized. Being in like middle school or high school, if you're good at math, it's like you're one of those people. You're one of the nerds. You know?
Oh, yeah, interesting.
You don't want to be one of the nerds.
So in other words, it's a way of stigmatizing the person who's good at math. Yeah, interesting. Interesting. Yeah, I'll tell you my own perspective. One of the reasons I think that it's an interesting joke is that it often points to the fact that people who can do math are often viewed as having special powers, right? In some ways, godlike powers. And in the presence of someone who can do math, those who have failed and fallen short feel unworthy in some sense, right? They feel like they've sinned. But you know, in many ways, there are lots of parallels between the way people practice math and the practice of religion. So I'm going to talk a little bit about that. And in making this point, I just want to be very clear. I'm not the first to say that there is a connection. In a 1921 speech, David Eugene Smith, another former president of the Mathematical Association of America, actually has spoken eloquently about the parallels between an attitude of mind that mathematics produces, as well as religious attitude of mind. And the point of this talk is not to use math to proselytize about faith, because I don't think that math contains the sole elements necessary to bring about faith in a person, nor will the faith that I refer to in these analogies necessarily be specifically Christian, although there will be some cases where I'll point out connections to the Christian faith. But rather, the point of showing parallels to start the discussion we're going to have tonight is to lend some plausibility for those who are inclined to faith that math questions can offer similar joyful pursuits, and for those who are inclined to math, which may be many of you, that faith questions are also worthwhile to investigate. So I think I'll first tell you a little bit about my own mathematical interests, and then I'll talk about the connection as I see between math and faith. So the kind of mathematics I do is actually an interesting mix of two different fields. One is topology, which you can think of as the study of stretchy things, and the other is the study of combinatorics, which is you can think of it as clever ways of counting. Okay? And the kinds of questions that I'm interested in actually combine topology and combinatorics, which may seem very strange because one feels very discrete, one is very continuous. And I actually am very interested in problems that come from the social sciences, so questions that have to do with how people interact in various ways. And one of the examples of this is of a topological theorem. It's kind of an amazing theorem. Is something known as the Breier-Fix point theorem. I'm not really going to do lots of math in this talk, but I'm just going to give you sort of a broad sense of some of the cool things that math offers. So the Breier-Fix point theorem is kind of an amazing theorem proved in 1912. And it says that anytime you have something that's like a ball, whatever that means, and you have a continuous function on the ball, then there must be a fixed point. Okay, so as a demonstration, the fluid in this cup is a ball-like. It basically has no holes. And if I slosh it around, then as long as I don't stir it discontinuously, that's a continuous function from this ball to itself. The fluid moves around, yes? So if I take a picture of this fluid and then slosh it around and take another picture, the Breier-Fix point theorem says that the amazing thing that there must be a point in the liquid that is in the same place in both pictures. You with me? It might have moved around in the middle, but there will be a point that is in the same place. And if I slosh it again and I move that point out of its original position, some other point moves back in its original position. Okay, so it's kind of an amazing theorem about the existence of some point in this liquid with a special property. Another way to think about the Breier-Fix point theorem is if I take a map of Pasadena, this is a map of Pasadena, and I crumple the map, as long as I don't tear it, and I throw it somewhere in Pasadena, then there is a point in the map directly above the point it represents in Pasadena. As long as I throw it somewhere in Pasadena, and as long as I don't tear it and throw East Pasadena into West Pasadena and West Pasadena. That's what the Breier-Fix point theorem says. And there's actually a combinatorial equivalent known as Sperner's limit, which I'll tell you a little bit about. And one of the most amazing applications of the Breier-Fix point theorem is a theorem from game theory known as the Nash equilibrium theorem. How many people here have seen A Beautiful Mind? Many of you have. The story of John Nash, and one of the things that he's famous for is a mathematical result for which he won an economics Nobel Prize, known as the Nash equilibrium theorem. So game theory is the study of mathematical models of decision-making, how people interact. And the idea here is that basically, what do players do? Players play strategies, and the idea of a Nash equilibrium is that's the existence of a pair of strategies where neither player has an incentive to deviate, to change their mind. So it's an equilibrium in the sense that if you have an equilibrium, you might predict that people will play it because their mutual best replies to each other. Okay? And of course, if you watch the movie, they get it completely wrong. And it's actually a fun exercise to watch the movie and figure out what they're saying wrong about the Nash equilibrium. But here's the amazing thing. It's a 3-page paper in a journal in which he uses the Brouwer-Fix point theorem to prove this theorem. And the basic idea is that the space of possible pairs of strategies is a ball. And if players have an incentive to deviate, it suggests a vector direction in the ball to move. And so the fact that this is a continuous function on this ball means there must be a point that doesn't move. End of story. It's kind of amazing application of a beautiful, beautiful mathematical idea. And my interest has been in solving problems where people have to divide things fairly among each other. The mathematical modeling comes in, the modeling of preferences over things like cake, but it could be more complicated things. And there's this theorem known as Sperner's lemma, which is true in all dimensions, but I'll just show you an example in 2 dimensions. Basically says if you have a triangle, which is, by the way, a ball, then in fact, if you break the ball into lots of pieces, this is the combinatorial piece, then label the corners of these little baby triangles by 1, 2, or 3 with a special property. This property is the corners are labeled different, 1, 2, and 3. And then the 1, 3 edge, you can allow labels 1 or 3, 2 or 3, or 1 or 2 on the bottom. Are you with me? And in the middle, you allow any of those labels. This is what's called a Sperner labeling. And what Sperner's lemma says is that, in fact, such a labeling must have something special happen, namely, there must be 1, 2, 3 baby triangles. In fact, there must be an odd number, which means non-zero. An odd number is never 0. So there's at least 1. Okay? All right, so a very innocuous looking statement, but it turns out to be completely equivalent to this powerful theorem in topology. This is why I've been attracted to this. I'll just give you an idea of how you show this. It's kind of amazing. It's beautiful. It's awesome. Oh, I just gave away the proof. Well, here's the proof. Here's the cool thing. So if you notice, because of the labeling rules, there's a 1 here and a 2 here. Along the bottom, would you agree there's an odd number of 1, 2 edges? Yes? So if I think about every 1, 2 edge in the house, think of this as a house with many rooms, think about every 1, 2 edge as a door, then I can walk in a door, and if I see the third corner, if it's not a 3, it's either a 1 or a 2. So if it's not a baby 1, 2, 3 triangle, there actually has to be another door. So if you just walk through doors successively, you will either end on a boundary or you'll end on a 1, 2, 3 triangle. But because there's an odd number of doors along the bottom, at least one of them has to match up to a 1, 2, 3 triangle. And if there are any others, they come in pairs because of the path as well. Okay? Beautiful idea. If you just barely caught that, just remember it has something to do with counting, okay, and following paths. But what's great about this is this actually led to the first constructive proofs of Brouwer applications. So if you want to compute a Nash equilibrium for a highly nonlinear game, you can do it using this very simple idea. And the way it connects to k-cutting, I'll sort of give you an idea, is you break the space of divisions up into some little pieces, and you walk around using Sperner's law. And so here's how you do it. If you have a cake, you break it into 3 pieces. That's a triple of numbers that sum to, let's say, 1, and they are bigger than or equal to 0. So that's a point in a triangle. So every point in this triangle is a division of cake. This corner is the division where the blue piece has all the mass. This corner, 0, 1, 0, is where this piece is the entire cake. And this one is the one where this piece is the entire cake, yeah? And so if you break this space of divisions up into pieces, what you end up seeing is that, I could, for instance, assign, if there are 3 people I'm trying to divide a cake between, Alice, Beto, and Carlos, I would create I'd basically label the corners by one of those 3 people, A, B, or C, and then I'd ask them, which piece would you prefer if the cake were cut like this? And you record their responses. Those are labels. And the one corner, at this corner, you see that no matter who you ask at this corner, which piece are they going to prefer? Piece 1, piece 2, or piece 3? Piece 1 has all the mass. They'd answer what? 1. Piece 1. What piece would they prefer here? Piece 2. What piece would they prefer here? 3. What piece would they prefer all along the bottom? Well, that's where piece 3 is empty. So which piece, what would they answer here no matter who they are? 1 or 2. And you see, you get a Sperner labeling from their answers. And if you're just creative about how you label the owners, then every 1, 2, 3 triangle corresponds to an Alice, Beto, and Carlos triangle. And so what you find is that there is a point that actually, a division, if you take smaller and smaller triangles, you get a division that satisfies everybody in an NB-free way. Kind of a nifty idea. If you didn't catch that, just enjoy the sense of And I got interested in this question because my roommates in college, one of my friends in grad school had this problem. Hayden split the rent fairly, and I proved a theorem that says, gave conditions under which you can split the rent in an NB-free way with very reasonable conditions. And if you'd like to try it out, you can check out the New York Times app, actually. Somebody contacted me from the New York Times recently, and they said, we came across your research, and guess what? We'd like to do this as a New York Times interactive. So they actually built a nice app which you can try out to divide your rent fairly. You can try it out. Okay, one of the recent things that I've been doing, which is kind of amazing, this is my own word. I mean it's amazing because I think it's beautiful, not because it's going to change the world. But it might. Is actually asking the question, if you have multiple labelings, how do those labelings interact? And I won't explain exactly how, but I'll just tell you one very cool application of this theorem. To fair division, it's what we like to call the survivor-style cake-cutting theorem. So here's an amazing theorem which we just proved this past year. So it turns out that if you have a cake, not only can you divide the cake in an NB-free way among n players, that's the usual cake-cutting theorem, but this totally blew us away when we realized this is true. There's actually a way to divide the cake, if you have n people, to divide the cake among n-1 into n-1 pieces, so that no matter who you kick out tonight, you'll still be able to make everybody happy tomorrow. Oh, interesting. Didn't know that was possible. Okay, end of math interlude. But it does, I think, point to some things which I want to refer to in the second half of my talk, which is that math actually is full of profound ideas that are beautiful. And what I want to talk about is basically 2 things. I want to talk about beauty and I want to talk about truth. Okay, these are all these are desires that all of us have and all of us seek in various ways. And some people seek them through mathematics. And I want to just highlight the fact that mathematics, the pursuit of mathematics for its beauty and its truth has many parallels with the way people pursue religious belief and religious faith. I want to talk about it. I love this quote by Blaise Pascal, which says that truth is so obscure in these times and falsehood so established that unless we love the truth, we cannot know it. It seems really appropriate for today, actually. This is an illustration by my friend Carl Olson, who's illustrating a book that I'm writing right now, and this is a chapter about truth, although it's not directly related to math and faith. It's related to math, but not necessarily related to faith. But I love this picture because it shows how much we crave truth. Truth is like a pearl of great price. So, when I talk about the immortality of mathematical truth, that's one way in which has religious parallels. What I mean by immortality is that I mean two things. I mean that mathematical truths have a certain permanence in both space and time. Right? There's no corner of the universe in which the Pythagorean theorem does not hold. And if you get bored in this talk, this is a proof that the Pythagorean theorem is true by matching up pieces in a big square with pieces in these two squares. There's no corner of the universe in which 1 plus 1 does not equal 2. Right? So there is permanence of mathematical truth in both space and time. The theorems of math will never be overturned. Right? Mathematical ideas themselves have a permanence that is both attractive and beautiful. And if you think about the physical sciences, yeah, there's laws. You have nature's laws, which usually refers to facts that are empirically observed to be true over many instances. But as you know, in physics or chemistry or any of the physical sciences, sometimes these laws can be overturned by new knowledge. Right? We have a certain maybe incomplete understanding. We have a better understanding and realize, oh, these laws aren't always true. But when a proof in math establishes a theorem, that will never be overturned. So there's something very permanent about that. That theorem is true for all time, and it's true everywhere in the universe. Sperner's lemma is true everywhere in the universe. The theorems that I prove will always be true. It may someday be irrelevant, but it'll still be true. And so this kind of permanence is unique to mathematics, and this kind of permanence offers hope, at least for me, that there are other kinds of things that are true, and their truth will endure for all time. So the quote that I had on the initial slide is by David Eugene Smith, who said, "Strange that in algebra we accept without the slightest question the idea of the permanence of law, mathematical law, but that our little natures should so often boast that we deny the permanence of the soul." And what he's saying is that mathematics suggests that we might be more humble about any claims that the soul itself could not be immortal. So this is an insight that math, I think, brings to me as a person of faith. There's another insight that I think math brings, and that's the externality of truth. There's a reality external to ourselves that interacts with us. Right? So mathematicians often think of mathematical truths as existing in their own reality. So if you sit back and think for a moment, what is a number? What is the number 1? What does that mean, really? Right? 1, it's not a concrete thing. It's not a dog or a chair, but it helps describe a single dog or a single chair. What is 1? It's a representation of a bunch of things that have a quality called oneness, right? You might think I'm speaking of a quality that's something subjective, like softness or redness, but in fact, oneness is a more fundamental quality that it's not subjective at all, right? Any alien creature would most likely understand the concept of oneness, even if it wasn't a natural concept for them. And once you've established what oneness is, then it always follows that 1 plus 1 equals 2. So no matter who you are, or where you live, or when you live, this reality exists. And so the way some think of it is it's a Platonic world, right? And it lives outside of ourselves, but somehow everybody has access to it, which is really strange. It's very strange. It's amazing that this reality would have anything to say about our world at all, but it does. So it's an unexplained power of math that these envisioned realities sometimes end up describing aspects of the physical world we didn't see before. Right? Who would have imagined that linear algebra ideas, which were developed in the mid-19th century, that they would find spectacular application in the mathematics of search engines or in quantum mechanics in the 20th century. Nobel Prize-winning physicist Eugene Wigner said this: He often spoke of the unreasonable effectiveness of mathematics to explain the natural sciences, and he said, the miracle of the appropriateness of the language of math to the formulation of the laws of physics is a wonderful gift to which we neither understand nor deserve. Right? It's possible. You can imagine another world where there's this thing called math and people just do it and it has no connection to the reality that we have at all. But it's an amazing philosophical question to wrestle with. So when and Einstein asked a similar question, how can it be that math, after all being just a product of human thought independent of experience, is so admirably adapted to the objects of reality? So when we grasp how surprising it is that you could have an external reality outside our universe that still interacts so deeply with it, it's probably less surprising that there could be a God outside our universe who interacts so deeply with us. Another aspect of math that I think relates to faith is the profoundness of beauty. Sofia Kovalevskaya was a well-known analyst, mathematician. She said it's impossible to be a mathematician without being a poet in soul. Another beautiful illustration by Carl Olson. So if you ask mathematicians why they study math, one of the main reasons you'll hear is because it's beautiful. Because it's beautiful. How many people here are studying math? Math majors or a few of you? No, okay, not too many are doing math, but many are doing math related. How many people are doing something math related? Yeah, that's probably it. It's Caltech. Yes. So one study even showed that mathematicians respond to mathematical beauty in a similar way to how others respond to visual, musical, or moral beauty, by activating a part of the brain that handles emotion, learning, pleasure, reward. And so there are many different kinds of beauty. I want to just touch on a few different kinds of beauty. The first and most accessible kind of beauty is sensory beauty. Right? This is the beauty of patterned objects that you experience with the senses: sight, touch, sound. And such objects could be natural, artificial, or virtual. Striking patterns and ripples of sand, the fractal pattern of Romanesco cauliflower. I was actually amazed when I was in England and I came across this cauliflower. I've never seen here in the States, but it looked like a fractal. I mean, it is a fractal. I was like, whoa, I didn't know this existed, and blown away. These patterns that we find in nature are all produced by mathematical laws. Music is an example of patterns, sound waves that produce feelings of sensory beauty. Artwork in every culture includes patterns, sometimes created by complex mathematical ideas. Quilting patterns are popular across the globe. And so the feeling of sensory beauty is similar to the feeling that nature evokes. Right? You feel joy, like walking through a beautiful forest. And if you've ever been to the Sainte-Chapelle in Paris and bathed in the dazzling patterns of sunlight streaming through stained glass, you'll know what I'm talking about. Architecture, music, because of their immersive mathematical natures, enhance feelings of sensory beauty. And in sensory beauty, you begin to esteem the order and the patterns that you see. Right? You become attentive to little details. Your soul quiets in much the same way that you would in a religious house of worship. And when you experience sensory beauty in the form of symmetry, smooth curves, and angles, aren't you just experiencing abstract algebra, calculus, and geometry in the wild? The second experience of mathematical beauty is what I like to call wondrous beauty. And I use the word wonder in two ways. Wonder in the sense of feeling awe, of seeing something amazing. But also wonder in the sense of feeling curious. Curiosity causes the mind to wonder, to be curious, to ask questions. And while sensory beauty usually concerns itself with physical objects, wondrous mathematical beauty always invites a dialogue with mathematical ideas. Right? So wondrous beauty can often follow from sensory beauty. If If you look at a beautiful geometric design, you might begin to ask, how was it made? If you listen to an uplifting harmony, you might begin to ask, why does it sound so glorious? Both how and why are the start of conversations with mathematical ideas. When you look at mathematical artwork, it causes you to speculate how its striking patterns were generated. You don't need to have answers for your questions to experience this kind of wondrous mathematical beauty. But wondrous beauty can also be independent of sensory beauty, right? When a mathematician looks at a beautiful equation like E equals mc squared, she isn't admiring it for its physical form. She's admiring it for the idea contained within. Somehow, energy and mass are interconvertible, with a small amount of mass equivalent to a large amount of energy. If she thinks this formula is beautiful, many people rate it as one of the most beautiful mathematical equations, it's probably because there's no obvious reason why the 5 of the most important constants in the universe happen to be related in this way. This is the surprise, the unexpected, that many see as an element of mathematical beauty. And it leads to wondrous beauty because you ask, because surprising things cause us to become curious and to ask why. I like this quote by historian of math Judy Grabiner. She said, musical beauty is a violation of your expectations in a way that afterward seems natural. That's what I think mathematical beauty is as well. So here you hear her referring to the element of surprise that often pops up when you study math. That something is true that you wouldn't expect to be true, right? Like the fact that there's a survivor-style cake-cutting theorem. That's amazing. And religious faith can sometimes be like this as well, right? There's some deep paradoxes in the Christian faith that somehow seem strange, but afterwards make sense. Like how a most powerful God enters the world in the weakest of all ways, as a baby born to a poor family in a nowhere town, part of a persecuted minority. This was certainly not the entrance that most people expected of the Messiah. Or how a loving God can also be a just God. If you think about it, we all crave to be loved. We all crave somebody of ultimate significance to love us. And yet, when we look around in the world as it is today, and we see grave injustices in the world, we often cry out, who's going to hold these perpetrators to account? Who are going to speak to the people in power who are abusing their power in unjust ways? We desire for a God or some ultimate source of authority to hold them to justice. So it's kind of a paradox. We desire justice, we desire God to be loving to us, and we want God to be just when it comes to other people. How can a loving God also be a just God? And the crazy solution, the unexpected solution, is to realize that we are the perpetrators of injustice, just like other people. We can't point the finger at others unless we first examine ourselves. And the crazy solution, God's solution, is for Jesus to receive the accountability for our sins so that he is both just and merciful. That's the unexpected, the surprise that I often see when I study questions of faith. Another kind of beauty in mathematics is insightful beauty. And this is the beauty of understanding, right? This is distinguished from sensory beauty, which concerns itself with objects, wondrous beauty, which concerns itself with ideas. Insightful beauty concerns itself with reasoning. Logically correct deductions are not sufficient for the mathematically minded. She often looks for the best proofs, or the simplest, or the most insightful, right? Mathematicians often have a special word for this, elegance, right? We say an argument is elegant. Paul Erdős, a prolific mathematician, often spoke of the book that God keeps, in which all the most elegant proofs of theorems are kept. Insightful beauty relies on elegant reasoning in the same way that the beauty of a poem relies on the words chosen. So insightful beauty often has a surprising feature that it depends strongly on communication, which should be an elegant proof, won't be elegant or lucid if it's communicated poorly. But when communicated well, it can move the soul like a poem. And this is why Sofia Kovalevsky spoke about being poets in soul, because we crave insightful beauty. And a common experience of that is to have this flash of insight, the aha moment. In mathematics, it's that thrill of sudden understanding when something foggy becomes crystal clear, like finding an elegant solution or illuminating proof. Right? The emotion that follows is the giddy excitement of seeing the big picture, when everything finally makes sense. Right? It's like that feeling when you're shopping of stumbling on a sale for an item you never knew you needed, that meets desires you never knew you had. Right? It's that feeling of watching the ending of a mystery movie, when everything gets explained. And just as people enjoy watching great movies a second time to see new details, a mathematician, or the mathematically minded, will enjoy dwelling a second time on the threads of an insightful argument, to think about its ramifications, its generalizations, or its applications. Now, it's true that clumsy solutions can also be found in a sudden way, but the emotion there isn't excitement, but relief that the ordeal is over. Right? Long-winded arguments tend to be clumsy and easily forgotten. It's no wonder why simplicity and lucidity of an argument is associated with beauty. Insightful beauty can manifest itself in a flash of insight or as a slowly growing appreciation over time. And there's many mathematical ideas that I didn't appreciate until I'd seen them arise over and over again in disparate places. Right? One recurring theme throughout math is the idea of duality, natural pairings that exist between mathematical ideas. Multiplication and division, sine and cosine, unions and intersections. Duality is like holding up an appropriate mirror in order to see that two creatures that look and behave differently are really the same. And I didn't appreciate duality until I saw it in many contexts. Now I think it's beautiful. And this happens in faith contexts too. I'll give you just one example. There's this idea of grace, which appears in the Christian faith. And grace is the idea that we don't earn our favor with God. It's one of the things that makes the Christian faith distinctive, is the primary emphasis on this idea that we don't earn God's love. God just loves us first. And what this means is that the love that we receive doesn't depend on anything that we do. It doesn't depend on us being moral. It doesn't depend on us being accomplished. It doesn't depend on us being rich or poor. So every person, weak or strong, poor or rich, has dignity and worth, independent of how they perform. And that's something that the longer that I follow Jesus is a powerful idea that affects and shapes every context in my life. Right? It's directly related to my academic life, that I don't get my dignity from my resume, that I don't get my dignity from how smart I am or how well I speak. And if I understand that God loves me for who I am, then it frees me, because I don't have to feel the need to perform all the time. I don't need to feel like I have to run the academic rat race that so many of us struggle with, and I still struggle with. But I have a certain freedom now that I realize I don't need my dignity from this. The people who love me, who truly love me, don't care whether I have a PhD or a degree from Caltech or Harvard. And so this is an idea that is now beautiful to me in a deep and a profound way. It shapes the way that I teach. It means that I can teach as a person who values the C student or the failing student just as much as the A student. And so these are all many different ways, different kinds of beauty. I think if you hang around math long enough, you begin to see that each of these forms of beauty can lead to an even deeper form of beauty. And that's the idea of transcendent beauty. Transcendent beauty it can arise from sensory, wondrous, or insightful beauty, but it goes well beyond. Right? Right? Transcendent beauty generally moves from the beauty of a specific object or idea or reasoning to some greater truth of some kind, perhaps an insight that grasps its deep significance or a deep connection to known ideas. And when you experience this kind of beauty, you feel a profound awe, even a sense of gratefulness. I like what Jordan Ellenberg says in his book, How Not to Be Wrong, The Power of Mathematical Thinking. He says this: what's true is that the sensation of mathematical understanding, of suddenly knowing what's going on with total certainty all the way to the bottom, is a special thing, attainable in few, if any, other places in life. You feel you've reached into the universe's guts and put your hand on the wire. It's hard to describe to people who haven't experienced it. This is the idea of transcendent beauty. And this is a desire that I think all of us have, to feel moments of transcendence. And when you look into another human being's eyes and you have a connection, there's a transcendent feeling of something beyond ourselves. This is something that we all seek. And mathematics in some ways offers a connection to the transcendent. There's so many mathematicians who talk about this kind of beauty. And I think this is the kind of beauty to be offered and to be found in religious faith. When you feel at a deep level that there is an external reality outside ourselves that interacts deeply with who we are and who we want to become. There is an ultimate truth. There is an ultimate beauty. Thank you very much.
All right, so at this point, we have just a couple minutes before we break into our table discussions for Q&A. So if you have any burning questions for Dr. Su as a whole group before you break into our discussion groups, feel free to raise your hands and we can ask those.
Yes, Dr. Su, would you describe a little bit of your own experience growing up, how you entered the math field of math, and where did that coincide with your spiritual journey?
Math, good question. I guess as a kid, I was attracted to the patterns of mathematics. So as a kid, you don't really know what math is all about. But I did like math as a kid, at least the versions that I saw, and actually was introduced pretty early to this problem-solving competition they have in Texas called Number Sense. I don't know if any of you live in Texas. But the cool thing was, it wasn't this problem-solving itself. It was that there was this book, this training book, that basically explained why all the tricks you were learning were true. And I was so amazed at this book. I was like, oh my gosh, you can actually show that Pythagorean triples are always of this form. It was amazing. It was kind of like, whoa. The fact that you could deduce that is amazing. And so that's, I think, what convinced me I should try to study mathematics. That was probably high school. Obviously, as you get farther in math, you realize, whoa, math is even bigger than that. And as I said, it wasn't through math that I began my journey to faith. It was other things. But now that I am a person of faith and also a mathematician, I see lots of consonants.
Thank you for your talk. I wanted to ask if you thought that doing math or mathematics in any way requires a degree of faith.
Oh, that's a great question. The question was, does mathematics in any way require a degree of faith? Yeah, I would say it does. Not necessarily religious faith, but it is, in some sense, a faith in the unseen, having the certainty of things hoped for, the assurance of things hoped for, in some sense. Right? Every time you do a mathematical proof or try to solve a mathematical problem, you're exercising a certain kind of hope that you're going to eventually solve it, and that this particular problem has a solution. And I think this directly relates to why mathematics education often stumbles in that we don't pay enough attention as teachers of mathematics to helping students feel that hope that they're gonna solve a problem. Right? So if you, for instance, have a person whose mathematical identity has been damaged in various ways by people who treat them poorly or dismiss their mathematical abilities or don't cultivate their own reasoning in the student rather than doing it the teacher's way, you are basically destroying their mathematical identity, and that leads to a loss of hope. So yeah, I guess that's the first thing that comes to mind when I think about the faith that we exercise as mathematicians. I mean, why solve a problem if you don't have hope that it's going to be solved? I mean, each of you are here at Caltech probably because at some point you experienced the thrill of solving a problem, right? And you know that when you think about something, you can actually think about it and reason your way through it. Yes. But I think there's a lot of people who will look at some idea and just not even realize that you can actually think about it. Right? Like that, like the other day I was talking to somebody about this trick for multiplying by, squaring numbers quickly, right? Or multiplying by 11 quickly. And this person didn't seem to be surprised that there was even a trick, right? Like you can look at a pattern, the patterns formed, and actually figure something out. Right? This is part of cultivating a mathematical identity that I hope all of us will cultivate. I think we don't pay enough attention to that, the role of hope in helping people learn math or science. That is an element of it.
So you liken the experience of proving a mathematical theorem to spiritual experiences, like experiencing love or grace. But in the former, there's a method for knowing that you experience something true. Is there a method for the other kind of experience?
Oh, great question. So the question is, if I liken mathematical pursuits to religious pursuits, in mathematical pursuits there's a method. That's the question, right? Is there some method in religious pursuits? Yeah, that's a great question. I would push back on that a little bit. I mean, I think the most interesting mathematical questions are ones which it's not clear what the right method is. Right? It's the unsolved problems that attract us, not the solved ones. And when you think about it that way, there's a certain creativity that you have to bring to attack the problem, to address the problem. And there's a certain despair that you feel if you can't solve it, right? And this is like questions in life. I have lots of problems in my life which remain unsolved, yes? And one of the virtues that I think mathematics actually builds in us, this is part of the dialogue between math and faith, one of the virtues that I think math builds in us is the expectation and hope that we will solve problems, even if it's not the current problem, right? That the effort itself will help us solve the next problem, even if it doesn't solve the current one. And part of what we bring when we embrace that to our faith life is that there are answers that we can pursue that are worth investigating, even if we don't answer this particular question. Maybe we'll answer another one.
You mentioned that there's sort of an external spiritual reality which you feel interacts deeply with our own reality. How did you, in your personal life, come come to feel that this external spiritual reality is the Christian reality?
Yeah, that's a great question. The question was, how did I come to feel or believe that the external reality that I speak of is the Christian reality? Yeah, that's a multi-layered question, but I think maybe probably the first level on which I can answer that is, I mean, I was a freshman in college. I was struggling with deep questions about life and meaning, and I was looking for hope. I had not seriously investigated other faiths at that time. I was just looking for a way out of my depression, in some sense, my despair. And what I understood about the Christian faith, I'd never opened a Bible, actually. But what I understood about the Christian faith as it was explained to me was the uniqueness of Jesus and the opportunity of grace. And I think at that point I embraced this message because it actually sounded like the unexpected solution, right? The idea that somehow we don't earn our favor. Like I always thought that Christians were, moralists who wanted everybody to be moral. And then I met these Christians in college who basically said, no, that's not actually the heart of Christianity. It isn't about being a moral person. It isn't about being holier than everybody else. It's actually the strange revelation that I actually don't have to be moral in order to be loved, but that I actually love they try to be moral because I'm loved, right? So the attempt to be moral is the consequence, not the prerequisite for being loved. That to me was strange. It went against everything that I had seen, but it actually made a lot of sense to me because who actually wants to run the rat race of trying to live up to being moral? Who wants to do that? That's not good news. And so I embraced it, and I prayed to follow Jesus, and I felt like, if there wasn't any external reality behind this, I'd probably find out pretty quickly. And then after that, I had experiences of being touched very deeply by God.
Maybe one or two more if there's just a couple last questions.
Have you ever faced any backlash in the mathematics community for being a person of faith? You had challenging conversations with people bring up your faith and ask you, how you believe in God given your mathematical background. So I feel like that is something that happens quite often in biological sciences. When it holds up in math.
Yeah, have I faced any hostility in being a person of faith in mathematics? I have not had any difficult situations that have been specifically because I'm a mathematician. I've certainly faced it in the academy from various other people in the academy, but not necessarily because I was a mathematician. And I think it probably happens less in mathematics, that there's a certain antagonism, because in other fields, depending on the field, I think there are often caricatures of Christians that people are reacting against, and those are well established in those fields for various reasons. So yeah, I can't say that I've had a large amount of hostility. I think the other thing that I think is important is, as a person of faith, is to have a certain humility about who you are and what you're and how you bring yourself to this community. And I think one way that Christians ought to be known in their community is as people who serve the good of the community. Right? It's one of the reasons why I have accepted the mantle of leadership in my mathematical profession, because it's a way for me to serve the people we shape the profession in a way that benefits everyone. And so I think that's a role that those of us who are people of faith, that we should try to take up in our communities. And if you do that, it's really hard for people to object to you trying to do good for others.
All right, last one.
You talked a little bit about the beauty that you saw in. You talked about the beauty that you saw in spiritual ideas like forgiveness and how Christianity provides you with emotional support when you were going through a difficult time in college. But what kinds of other ideas do you draw on from the basis of your faith? Like as a mathematician, do you ever feel the need to prove that what you believe is true, or what kinds of ideas do you draw on to prove that?
Okay, so I think the question was, what other ideas do I draw on as a person of faith that I find beautiful, or
To form the basis for your faith.
form the basis of my faith? Well, I wouldn't necessarily say I draw on. Are you asking me specifically about mathematical ideas, or just in general? Yeah, I mean, in general, I guess, as a person of faith, I pray, and I experience a contact with external reality in that way. Not always felt, but certainly a discipline that I think puts you in a place where you can receive. I should do more of that. I think reading scripture is an important way of establishing and understanding the truths of God. Certainly, there are lots of attractive ideas about the Christian, the things that Christianity teaches. Serving others, loving others, that's a radical idea. But that certainly appears in various forms in other religious beliefs as well, and also non-belief. But yeah, I think there are some distinctives about the Christian faith, and it's not always the ones that people think.
All right, great. Could you join me in thanking Dr. Sue?